right, so let's talk about Verilog. Okay, and now that we have seen diagrams, right, state diagram, truth table, right, for simple circuit, for simple FSM, we can get away with the truth table. But later on, for you guys to build more complex circuits, you guys still need to write Verilog. You also need to write FSM quite a bit in the next lab, actually. So here's the template, right? And we are going to declare the module, right? So in Verilog and some inputs and outputs, right? Reg, right? So this reg will be assigned in always block. So 3 important always blocks, okay? 1 for the next state, okay? 1 for the output, and 1 for updating the state. Okay? This is state flip-flops. For FSM, we always need 3 always blocks. Okay, so this is a template. This is suggested templates. Right, so let's take a quick look. Right, again, this is the pattern detector. Right, so we can define the module. Right, and this clock input. Right, we have reset. Right, let's talk about reset a little bit. Right, so because we have a signal over here. Right, to initialize everything, to initialize FSM. So we have reg. Right, so we have reg for the output. We have reg. So this is a 2-bit. Right, so this is a bit vector with 2 bits. So this notation, current state, right, next state. And we are using the labels here. Okay, so we use the parameters. And over here, in this case, we assign the encoding, right, explicitly. And actually, in many cases, the cat does not require you to do so. We have 4 states, right? Init, gal1, right? So gal11, gal11. All right. What does state FFs mean? It's going to be clear, right? So let's first look at this. So I'm going to ask you, like, which ones are the FFs? All right, so this is the declaration, and this is how we write the always block for updating the next state, right? So this is the next state logic. We can actually use this case statement. So this is one thing, this is one construct, which is very convenient to use, right? Instead of writing a nested if then else, you can just use case, right? So depending on where are we, right? So whether we are at init, right? Got 1, got 1, 1, so got 1, 1, 1. So we will do different things, right? We will update next state depending on the input and the current state. So this is basically what this always block is doing. So quick question for you guys. This is also sort of a reminder and also refresher. Right? We talk about sequential logic, right? Combinational logic, right? We can actually use always block to model either one of them. So in this case, is this combinational or sequential? What is the thing to check, right? So to quickly identify whether this is sequential or combinational. Sequential? Are you guys sure? So first, there's no clock, right? Right? First, there's no clock on the sensitivity list. Okay, that already smells combinational, right? No clock on the sensitivity list. But last time, I think in lecture 8, right, we did talk about in some cases. So if certain output is not assigned, right, under certain input combination, we may have so-called infer latch, right? If it's indeed assigned under all different kind of input combinations, then we have combinational logic, right? So can you guys look at as next? It is actually assigned in all cases, right? So default is like the fallback, right? Although in this case, it's actually not that necessary, right? Because we already covered 4 combinations. Make sense? This is actually combinational. Any questions about this? This is not quite sequential. First, this is definitely not a flip-flop, right? Because we are not sensitive to the clock edge. And this is not latch. So this is combinational. And we also talk about, right? So we have this combinational logic clause, right? To update the next state logic. Okay, so this is combinational. Next one, right? This is the next state combinational logic. Next one. So we also have output, right? So again, this is combinational. This one, right? Because out, right? Out is assigned under all possible conditions, and we are not really sensitive to the clock edge. So the last one, right? The third one. So third always log. So there we have a sequential logic, right? So these are the flip-flops, right? So these ones, so as current, so this is going to be inferred as flip-flops, right? So these are the state flip-flops. Basically, we use these flip-flops to hold the state. Is it clear? Any more questions about the state flip-flops? No? Okay. And also another interesting thing is we have the reset over here, right? When reset is 1, we basically reinitialize, right? We reset the whole circuit, reset the whole FSM back to the init state. We have something called synchronous reset here. I think there's a question on Piazza about synchronous reset and asynchronous reset. There's also some discussion in the textbook. Right? In our class, we mostly use synchronous reset. So meaning that, so we only reset circuit at this is transition edges, right? At the triggering edges. Okay. So we don't. There's actually another style called asynchronous reset. There's pros and cons with synchronous and asynchronous reset. So this is not something that we need to worry too much about in this class. All right, so this is more machine. Okay. So I'll show you guys the Verilog simulation later. I'm gonna switch to another screen and show you this EDA playground. Okay. Let's also quickly look at the Mealy machine. So here we have 3 states, right? Pretty much the same, right? You know, we declare this current state, right, next state, and we have the encodings, right, for the state labels, right? These are basically like the enum, right? So construct that you guys use in other software programming languages like C or Java. And this is the combinational logic block, right, for updating the next state, right? So this is very similar to the Moore machine, right? We look at the current state, we look at current state, and then we look at input. Right? We can do if then else under each case, right, for each state. With Verilog, you guys can also do a nested if then else. You can actually write a begin end to do arbitrary level nesting. And we have the output logic, right? But for the output logic, so for a Mealy machine, we do have this, right? So we do need to check the input in addition to the state, right? So again, we are doing synchronous reset here, and then we update the current state, right? Every clock cycle, we assign the next as next to as current. So that's how we update the state. That's how we advance the state machine. All right, any questions about state machines in Verilog? If not, let's take a quick look at the waveforms. Okay. All right, so hope you guys are seeing a different screen, right? So I'm coming back to this website again, EDA Playground. So I've already entered my state machine. This is a Moore machine. Okay. So over here, and these are the test bench, right? So that's where I create some, this input stimuli to drive the test. So let's run the simulation. Okay, so this is a waveform, right? So see here, so this is my state, right? So this is actually the flip-flop, right? So at each clock cycle, right? It's actually initially it's don't care, right? It's not it's not initialized reset yet. So we have the synchronous reset here, right? So here there's a reset, right? Look at this, right? So the synchronous because we only reset circuit at the clock edge, right? At the trickle clock edge, in this case, rising edge. So before the rising edge, the state is not initialized. After rising edge, it's initialized to init state, which is 0, right? And then at each clock edge, after each clock edge, right? So we advance to the next state, right? From 0 to 1, 2, 3. And after a few cycles, actually 3 clock cycles, right? So we have a 1, 1, 1, right? So this is input, right? Input is high, right? All the time until here, right? And output becomes high over here because this is a 1, 1, 1 detector, right? Okay, so this is a Moore machine. Any question about this? If not, let's take a look at the Mealy machine quickly. All right, so this is Mealy machine. So once again, 3 always blocks, right? Next state, output, and updating the current state, right? Updating the flip-flops. So we can also run the simulation. Okay. So in this case, right? So we have Mealy machine, right? So remember we have 3 states, right? We go from 0 to 1 to 2, and for this Mealy machine, right? Since output is actually combinational to the inputs, right? So the moment we see the third one, we are actually raising too high, right away here, right, in this output state too. Okay, right. So this is the difference, right? And then we're going to stay at this state, right, for a while, since we are detecting overlapping ones. Okay, so this is the simulation. Let me come back to my other screen. This one. This one. Okay. All right. Hopefully, is it clear enough, right? So there are some questions, right? So why is it not parameter 2, 0 Lorentz sourcing, right? Why is it not 2, 0? Because we only need 2 bits, right? Right. So 2 column 0 means that we have 3 bits. Right. We only need 2 bits to encode 3 states. Right. 1 column 0 is sufficient. All right. So this is also another problem, right? So that we saw last time. We also looked at this push button log, right? So where we have 2 inputs, right? We detect the sequence, right? If this button is pushed, right, after this button, the other button X2 is pushed twice, then we unlock, right? I'm not gonna go over the state diagram again, so just wanna show you guys the end product, right? So that we drew last time. So this is the Moore machine. Right? This one is slightly more complicated, right? Since we have 2-bit input and 2-bit output, but this is a Moore machine, right? So we do put the output right in the state bubble, and we can also come up with the state encoding like this, right? So we have 4 states, right? 0, 0, again 0, 0, 0, 1, right, all the way to 1, 1. This is the state diagram for push button lock, for Moore machine, for Moore diagram, and this is the corresponding table, right? Transition output table using the label names. Okay. I'm gonna just quickly go over this, right? Since this is actually very similar to what we just saw with the pattern detector. And we can replace them, right? So with the 0, 1s, right, with the encoding, and this is a complete truth table, then we can try to minimize it, right? And try to derive the circuits. Okay, so the Moore machine, and we have also drawn the Mealy machine, and it's something like this. Right. Again, the only difference is the output, right? Oops. The output is showing up on the transition aux. Okay, and this is the diagram. Okay. Now the diagram, this is the table for the diagram. Okay. All right, so any other questions about this transition output table before we move on? Okay, if not, let's quickly talk about another direction. Right, so we have been looking at how to convert a problem, right, into state diagram, and then convert that state diagram into circuits. Right? So let's now look at the opposite direction. So if I give you a circuit, so can you try to come up with a state diagram and try to analyze it a bit? Right? So by circuit, I mean the sequential circuit, right? Since FSM is used to model sequential logic. Let's start with something very simple. D flip-flop. Okay, so how many states do we have? First, is this a Moore machine or Mealy for D flip-flop? Is it Moore or Mealy? So what is the output? Output is Q, right? Okay, we have I'm getting mixed signal here, right? So someone, it's good that we have some divided opinion, right? So this is gonna trigger a lot of interesting discussions. So what is the output here? Q, right? And Q equals what? So maybe let's just draw the Moore machine, the Moore diagram first, right? How about that? Okay. And hopefully it's going to be more clear, right? So this is the state diagram, right? Let's just draw the Moore state diagram like this. Hopefully you guys agree on this one, right? So I have two states. So in each bubble, right, which output either 0 or 1, right? And based on input D, right, we make the state transition. No objection on this diagram, right? So then we can draw the table, right? We can try to analyze it, right? If we have this, already have this state transition diagram. So we have output Q, right? We want S star, right? And we have S. 0, 1, right? So what is Q in the first row? Oh, let me divide this. What is this? 0, right? What is this? 1. So what is Q? In terms of S and D, what is Q? Do we care about D? S, right? Make sense? Right? Okay. So, because indeed this is right. This Q only depends on the current state, right? But then what's the next state, right? So this is where we can further divide it up, right? S star, right? What is this entry? S star. What's this one? 0, right? This one, 1. Okay, this one, 0. Okay, this one. Just look at the transition, right? 1. So what is that star? In terms of S and D, just D. Okay. All right. So hopefully this makes sense, right? So this is very much a Moore machine, right? Okay. Q only depends on the current state. S is the current state, right? Okay. And later on in the homework and maybe in the exam, right? So we will make the distinction, right? So when we look at circuit, we can directly tell whether this is a Moore machine, right, or Mealy machine. But actually, there's something a little bit confusing, right? Actually, we can convert any Moore diagram into a Mealy diagram, and vice versa. So we can actually do this kind of conversion. Okay, this is something that we may practice a little bit, right, in one of the homework. But hopefully this makes sense, right? So we can actually derive a diagram, right, for the D flip-flop. So if you actually want to make sense of it, right? So try to make sense of the actual, right, the correspondence between the output and current state, and next state, and the input. So we can just write down the table, right? Okay. I was just using question mark, right, to indicate which entry I was looking at, right? No, don't worry about the question mark. Right? So I was first writing down the question mark, right, and then ask you guys what was the value. Okay, so this is a very simple circuit. Okay? So let's look at something. Again, the clock is implicit here. Okay? Let's look at something more complex. Okay? Maybe this is something that I'll just ask you guys to complete as exercise. But let's try to make some sense out of this first. First, is this a Moore machine or Mealy machine? Very good, right? Jacob is saying Moore, and Mitchell, and hope most of you agree, right? One more time, look at output, right? So what is out? Can you guys tell me? What is out? S0 and S1, right? Out only depends on current state. So this is indeed the Moore machine. Okay. It does not depend on any one of the signals related to the input. Okay. But what exactly is the circuit doing, right? So actually, in some cases, we can try to make sense of something complex like this, right? So what does this do? So how do we go about this? So we already know that, right? Out is S1 and S0. So maybe you can also try to figure out what exactly the next state, right? What is S0 star? What's this? Okay. Right? In not, right? This S1 star is more complicated, right? I need your help. Can you guys tell me the expression? Just an exercise for you guys to read the diagram, right? Because in Prim 1, we may need you to read diagrams. So when we have T, right, junction like this is assumed to be connected. So these ones are supposed to be connected. And we have a cross like this is not connected. Okay, so I'll trust you guys, right? In not S0. Is that right? Is this correct? This is what Jacob proposed. Okay. All right. So Jacob is saying Paul's version is correct. Paul's version is this, right? Let's see. Okay. All right. Good. The chat window is updating quicker than what I can follow. This one. Is it correct? This. Okay. All right. So once we have this, then what do we do? What do we do next? Can we reconstruct the state diagram? From the circuit, how? What's the next step? How do we construct the state diagram? Determine S0 as 1. Yeah, it's close, right? So yeah, we do need to determine S0 as 1, right? So it needs to be somewhere, right? Yes. So Sebastian, you're right. So we need to construct this truth table, right? Transition output table. Once we have a table, we can reconstruct the state diagram. And this is what we're going to do, right? And basically, once I give you a circuit like this, right? So you derive, first determine is this a Moore or Mealy, right? Then you draw the corresponding table. So in this case, we have Moore machine, right? So we draw the Moore table, this transition output table. Okay, I have already completed part of the table, so I'll ask you guys to complete the rest, right? This is not a quiz, right? So just for fun, right? Just try to complete it. But over here, right? So I just want to remind you, so we do need, right? We do need to write down the current state S1, S0, right? We need to write out, right? So this is easy, okay? Since this is just an AND gate, right? We can quickly fill out the output column, right? We can also quickly fill out as 0 star, I suppose, right? Since this is just the inverter. So all you guys need to do is to fill out as 1 star, right? Fill the rest of the table for as 1 star, and of course as 0 star. So once you have that, you should be able to complete, right? So the rest of this transition, right? All you need to do is to fill out transitions, and hopefully you can later tell me, right, what exactly is this FSM doing? Okay, maybe it's a pattern detector, just a hint. All right, any questions? Okay, so if not, we can just wrap up here today. Once again, so we have a review session right tonight at 7. It's going to be recorded. And also, I believe Lisa has also announced some additional office hours over the weekend, right? So make sure to check out Piazza. And we have already canceled the last sessions on Monday. Right, okay. See you guys next week. Good luck with the program.